Well, hello everybody. We're going to be beginning our notes on acids and bases. You've probably heard the term pH. That's for a measure we'll find out about how much acid is in something, or it can be base. There's also a term pOH you probably haven't heard, but you have now. So let's get started here. That titled up there. So first off, let's do Roman numeral 1. Let's get a few definitions here about what an acid is or is not. I guess I'll scoot over there a little bit. So first off, definitions. Make that so you can see it. Now, for my substitute teacher, at any point if students need you to pause this, don't push the pause button, push the enter button. Okay, so if you need to freeze this for a moment, hit the enter button, and then when you're ready to play it again, hit the enter button again. So, acids and bases can break down matter. That's a fairly easy definition. Acids and bases can break down matter. Acids and bases can break down. Oh, okay, I messed up the down there. Sorry about that. Matter. And am I going off the page here? Let's see. Yeah, I better zoom out a little bit. I mean, we have acids that are inside of our digestive system that help us break down our foods. Now, there are three definitions of acids that we're going to go over. And the first one is called the Arrhenius definition, named after a scientist named Arrhenius. And his name's a little unusual for us to spell, so A, I guess we should call it. That's appropriate that it's Arrhenius. A-R-R-H-E-N, so like pirate, R, then hen, okay, then Eus, I-U-S. So, the Arrhenius definition, or Arrhenius, excuse me, Arrhenius. I pronounced it incorrectly for years. Arrhenius definition. So, an Arrhenius acid or base. So this is one of the first ones that came up. So, and I'm going to abbreviate on here that acids, okay, just to save some. Acid will equal capital A, base will equal capital B. That'll save us some time. I'll zoom in a little bit. So let's see. Acids will form a hydrogen ion in water. So acids form hydrogen ion. Now if we need to write that down there. Hydrogen ion. Acids form hydrogen ions in water. So for example, the hydrochloric acid that we have in our body, which we can write it as HCl, when it's dumped into water, it can ionize and you get hydrogen ions, which is an acid, and then you're going to get chloride ions, which is not an acid. So that's an example right there. Now bases, let me slide back over here. Bases form hydroxide. That's OH. OH with a -1 charge. That's called hydroxide. I'll put that. Hydro, or then the O part is also oxide. Hydrogen and oxygen. They form hydroxide ions in water. Now in this unit, you just need to get to know this is hydroxide ion, that is hydrogen ion. That needs to just be just kind of a given. And an example would be, now this would be like a lye, L-Y-E, which is pure sodium hydroxide. If you put it into water, it will ionize and it will make sodium ions, which are just kind of there. But it's also going to make hydroxide ions, which is a base. And now bases can be just as dissolving and deadly. If you were to fall in a big vat of base, it would be just as bad as if you fell in a big vat of acid. They both dissolve matter. They just do it in opposite ways. They use this a lot in the food processing industry. A lot of times, like with peaches, they'll dump peaches into some lye solution, sodium hydroxide, and that'll, for a moment or two, to help dissolve the outer layer of skin. So that's something where you might have seen, they might use that. Now, so there's our first definition. Now that was okay for a while, but scientists began to find out, hey, not every acid makes hydrogen ion, or not every base makes hydroxide ion in there. Now, if this is a time where the students need a quick pause or so, hit the enter button, and then we'll go on to definition B. Okay, definition B. So we're going to come over here. So some guys came along a little bit later, and a couple of different scientists, and they call this the Bronsted-Lowry definition. So one gentleman's name was Bronsted. And we'll put a dash there, Lowry. So what these guys, they modified this a little bit because there were some examples where this didn't work. So what they said that acids are proton, we'll put a P with a plus if you like. Actually, we can write proton over here. Proton equals, that's kind of going back to the beginning of our school year here, but acids are proton donors. Now, do you remember what a proton is? Yeah, it's a particle. Well, let's look at this guy. A hydrogen ion is just a proton. Okay, because if you take just a plain old proton right here, okay, with this plus charge, that's the same thing as a hydrogen ion. So we're kind of working with the same stuff. Anyway, so acids are proton donors. Bases are proton, what do you think? You got it. They are proton acceptors. They accept a proton. And we'll draw a little reaction here. Let's put NH3. This is ammonia. We use it diluted as a cleaner. Let's say we're pouring some ammonia into some water. And what's going to happen is you're going to have what they call dissociation. This stuff is going to kind of break apart. And then what's going to happen is you're going to end up getting what they call ammonium ion, which is NH4, and it has a plus charge. Ammonium, A-M-M-O-N-I-U-M, ammonium ion. Okay, remember, anything that has a plus or minus charge is an ion. Plus, what we're going to get is a hydroxide ion formed in that. So here's what's happening. When we come look over, when we first mix these chemicals together, what happens is that a proton is given up. This hydrogen, this water will release a hydrogen because it's pulled over basically by this. So a proton will move from here to there. Now, since this is giving a proton, that means it's a proton donor. And in this example, the water will act as a Bronsted-Lowry acid, okay, because it's donating a proton. Over here, the ammonia that's in the liquid, it's accepting this proton. Because see over here, when we're done with the reaction, it's got an extra hydrogen over there. So this one, by the definition of Bronsted-Lowry, the ammonia is a proton acceptor, and it's a base. Oh, great, the phone is ringing. Well, I'm just not going to answer it right now because I don't want to stop this lesson. So that's a new definition for what acids and bases are from the Bronsted-Lowry definition. Now we're going to do one more. There's another one. And this one is called the Lewis acid-base definition. Oh, it's amazing how long that phone rings when you don't want it to. So Lewis, acids, and bases. So this is kind of getting back into, this deals with pairs of electrons. So what we're going to say here, for a Lewis acid, acids are electron pair acceptors. I'm going to put electron E with a minus sign there. Electron pair. So there's a pair of electrons. Acceptors. Okay, that's what acids are defined as by the Lewis system. And then bases. Okay, think you can figure this one out? Because remember, acids and bases, they react, they operate oppositely. They're going to be electron pair donors. So they're going to donate a pair of electrons. So we'll do an example of this one. So let's say we've got something like NH3 again, what we had up here. But we're going to draw out the structural formula for it. So we've got NH3 like that. Now, when we went back and would have done the Lewis dot structure, hey, look at there, Lewis dot structure. That's the same guy. We're going to put, there's a pair of shared electrons because nitrogen is in group 15. So when it started to do the Lewis structure, we would have had 1, 2, 3, 4, and then the fifth electron got there. So here's a pair of electrons right there. And so what's going to happen is, let's say we take a compound like, let's say, barium fluoride. Excuse me, boron fluoride, my mistake. Now, boron is in group 3 of the periodic table, so it's only going to have, when we do the Lewis structures, it just have 3 dots over here because it's fairly small. So what will happen is, we're going to draw this over here. So these pair of electrons will be donated to this guy over here. Okay, they're going to kind of share those. Now we're getting in, you just really need to know, be aware of the Lewis definition. We're not going to make you be tested on this on the test. I just want you to be aware of it. When you, those of you going into AP chemistry, you'll be doing this some more. But what's going to happen here is, now you're going to end up with, here's the ammonia that we started with. Okay, but it's going to be teamed up now with the boron trifluoride, like that. And so what happens is, since this one right here is donating a pair of electrons, that means this is the base. And ammonia is a well-known base, or ammonium hydroxide. And then this one here, since this one is accepting a pair of electrons, okay, and here's where they end up, you see, those pair of electrons end up being shared between them, but this one's accepting it, this one would be called the acid by definition there. So there's those definitions. Now, if I'll get this adjusted very nicely in case the students need a moment to get that all recorded. Sub, you can push the enter button, and then we'll get going on with Part D. All right, Part D. Okay, and we're back with Party. Okay, we got Part D coming up. All right. Oh, wait a minute. Sorry. There we go. Part D. pH. We've been waiting for this one quite a ways, I know. So pH, you've heard this quite a bit. Probably had some labs in middle school where you might have seen a commercial where they say, this shampoo is pH balanced to be gentle on your hair. All right. Remember these charts right here? This is a pH chart. This chart is showing, remember that scale? It goes from 0 to 14. Okay, this is probably new stuff. We'll go over that in a little bit. But you remember neutral, and we said if you had a pH of 14, you were a very strong base, blue for base. And then if you had a pH approaching 1 or 0, you were extremely strong acid. So they're just kind of a little blast from your past. Anyway, pH is a measure of the hydrogen ion concentration. So, a measure of the hydrogen ion concentration. Now, I want you to notice these brackets right there. Now that we've studied the solutions unit, chemists are lazy. Okay, we've learned that's why they made these symbols in the first place. Okay, chemists are lazy. They don't want to always write like what the molarity is. So what they do is, if they ever say something like this, hydrogen ion with these brackets. What that really means is, that means how many moles per liter or molarity. So they may, if they write a number, it says like the hydrogen ion concentration is like 0.01 and it's in brackets like this, they're really saying that when you see that square bracket, that means the molarity of this solution is 0.01 moles per liter. So there you go, another shortcut for chemists, okay? See, you're getting sharper and smarter all the time. Isn't that cool? Because now you'll look at your book and you'll say, oh, I've seen that all the time. I mean, you know, all the time it's there. So we're going to get to that. So that just means the concentration in moles per liter. So, okay, our pH scale, we'll use colors here. You have neutral. Remember what the pH was for that? Come on, I know you know it. Put that cell phone away. What is it? Yep, 7. And then blue for base. So I'm going to put a very strong base over here. What's the pH of the base? The highest one you could get? Well, hopefully if you said 14, you are correct. So we've got the beginnings of the scale going. I always like to have acids. I don't know why, I just do when we label lab equipment. Acids, I tend to do in red. And the lowest pH, usually the pH is 1. I think technically you can approach 0, but we'll just say it's 1 to 14. Okay, we'll put a 0 there because in some of our stuff we'll have that. But anyway, so we have this range of pH. So if we say the pH is 1, make sure we know that's a 1, that's a really strong acid. If we say the pH is 14, it's a really strong base, and if it's a pH of 7, it's neutral. Now, here's the equation we're going to use. See, do I have enough room on this sheet of paper? Let's see. I think I do. Do I? I'm going to just go to another sheet of paper because I've got something. So if you've just got a little bit of room at the bottom of your paper, I need a little bit more than that, I think, for this. So I'm going to go, the next section is A, and it's going to be called pH. I know it says pH, but we're going to give the equation. So I'm just going to come over to here. So I got plenty of room. A, pH. Here's the equation. pH is equal to, let me zoom in because you really want to get this. pH is equal to the opposite, so we're going to put a negative sign, of the log. Okay, you've had that button on your calculator. It says log. Now you're going to learn how to use it. And now we're going to put the square bracket and put hydrogen ion. So if we have a hydrogen ion concentration, like maybe it's 0.00001 moles per liter, we will put that in our calculator. You hit log, and then you'll get a number. And then it'll probably be negative, and then you're going to change the sign. Oh, did I get everything there? So let's label this. This means the opposite of, or change the sign. Opposite of, or change the sign. So that'll make sense in a moment. Log. Oh, this is a pretty cool function. Now, what the logarithmic functions do, they convert extremely large numbers, like millions, billions, trillions, or extremely small numbers, like 0.000000001. They convert them into numbers that are easy to graph. So, log converts large or small numbers into easy to graph, to smaller easy to graph numbers. Into smaller easy to graph numbers. That's not a hashtag, that's numbers. For example, oh wait, I'm going to get things finished, get things labeled. And then the brackets here, that means moles per liter. That's a concentration. That means moles per liter, or our friend molarity. Okay, so that's what that means over there when you see that. So for example, let me get a calculator here, just show you what I mean. Let's turn on this calculator. I'm going to put in a really small number. Let me get that out of the glare here of the camera. Okay, so I'm going to put in a really small number like 0.0000001. Okay, so let's see. We've got we got a decimal place in 1, 2, 3, 4, 5, 6, 7, 8 spots before we get to the 1. Now here's what if I asked you to graph this, that'd be really a pain because that's a really small number. So if we use this logarithmic function, here's log. So the log of that number, when I push it, it really comes down to how many decimal places there are. So I'm going to push log. So we went back 8 decimal places, and the negative sign is telling us it's smaller than 1. So there, take that. So that's a much easier number to graph than 0.0000001. Clear. Now, if we were making a pH, let's say we measured and we found out we had a hydrogen ion concentration of 0.00000. Okay, did I push the right number of ones? Like that. So what we do is, let's say that's the concentration in moles per liter. We would hit log. Now we're going to get -7. Now we got to change the sign because remember right here, this equation, oh, where is it? I'm too zoomed in. That means change the sign. So on my calculator, there's this little change sign button. I'm going to push it, and that means that's a pH of 7. So that's how the log function works. It takes really huge. Okay, watch this. Watch this. Let's do this. Let's do Avogadro's number. 6.02 times 10 to the 23. Let's take the log of Avogadro's number, and what do you think it's going to be since we've got 23 zeros in there? Let's take the log. Boom! Look at that. It's 23.7777. So that basically means there were 23 sevens, and then the decimal point, then there were some numbers associated with that. So that's kind of cool. So let's zoom out. So now you finally know what that log function is, and it's really good when you're working with things that have really huge numbers. So, for example, let's draw this simple little graph. I'm going to do 2 of them here. Let's say we were making a graph of acidity, 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 like this, and molarity. Okay, this is moles per liter, and acidity is going to be pH down here. So let's say we were making a graph of this. What would happen is, as we increase the molarity, the acidity is going to increase. It'll be like, let me make sure I get this right, really low, like this, and then up like that. Oh wait, did I draw that backward? Oh, I'm going to be so mad if I drew that backwards. Did I draw that backwards? Yes, I did. Oh, I hope you used a pen. Oh, you're going to be so mad at me. So molarity versus acidity, pH, it's actually going to be like this. Okay, so this is how in the real world that graph would look, okay? Now the problem is these get to be really small numbers, but if you use a logarithmic function, what happens is when you go to plot it, it makes it a straight line, which is way easier for you to figure the slope of, which people in math and physics love to do, is figure the slope of the line and stuff. That makes it easier when you turn anything that goes to, they call them asymptotal, if I got the right term, meaning that these things approach 0 but never quite make it. A logarithmic function gives you a nice straight line that's easy to work with. So but when you do this, that basically means you've got molarity now versus pH over here, the log function over there. Anyway, it just makes it easier to graph, and that's why they use it. You're not going to need to use that too much, but it's nice to know how it works. So let's see. For example, over here, let's make a little data table. We're going to make a data table that's molarity, which is moles per liter. I'm going to zoom in here for you. So let's write down some molarities. Let's write down a molarity of 0.1. Let's do a molarity of 0.01. Okay, this is getting to be really a diluted solution. And let's do 0.001. And let's say that this was molarity of hydrogen ion, okay? Molarity of hydrogen ion, which I guess we could say in this point, we're going to put square brackets around these. And that's telling us this is the molarity. They're getting to be fairly small. So what happens is, let's do this. We'll just go there. When you go through and figure out the pH, this 0.1, this turns out to be 1, a pH of 1. I'll make sure that says pH. when you plug this into the equation, you're going to get a pH. If you don't believe me, you can do it. You can have fun. You can show your parents at dinner tonight how cool it is, and you can figure out logarithmic functions. So it just takes a really, and potentially really smaller numbers as these get to be point, like if we do here, 0.000000001. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's going to be, boom, pH of 9. Oh, I guess you need that. Okay, you don't have to write that one. I'm just giving you an example there. So we're almost done. I know this has been kind of long here. We're going to see a really cool video here in a moment. So this was part A. Okay, our subheading A under pH. Now we're going to do subheading B. This goes really quick. Almost done, I promise you. So this is called POH. Now you don't have to do the equation, because really the equation is going to be exactly the same as that one, except it's going to be with OH inside of their concentration. So POH is a measure of how much hydrogen hydroxide ion you have. MEA, measure of how much hydroxide ion of how much, there you go, hydroxide ion. And that's going to be, so let's see. So what do I want to say on this? So I'm not going to go replot this because it's pretty much the same. It's just going to be, what's interesting though is that pH and POH, they all have to add up to a magic number of 14. So that's what we're going to put here. We're going to say pH plus POH. If you add those up, they're going to be 14. So if you have a solution that's a pH of 10, okay, let's say we had a pH of 10. What would the POH be? Well, let's see. This is pH 10. Whatever the POH is, when you add those up, they have to equal 14. So why don't you figure that out there real quick? What is, 10 plus what is 14? Yeah, you got it. The POH would equal 4. So there's that. Take that. Now, almost done, but not quite. The hydrogen ion concentration that we talked about earlier plus the hydroxide ion concentration, they will always, when you add up those two, they will always add up to 1 times 10 to the minus 14. Now it's kind of funny, if you put this in your calculator, 1 times 10 to the minus 14, and then hit log, and then take the opposite of it, you're going to get 14. So if we said to you that we had a hydrogen ion concentration of 1 times 10 to the minus 4, so that's 0.0001, what is the hydroxide ion concentration? Well, they're always going to add up to this. And by the way, if we just have 1 times 10 to the minus 14, usually we just shorten it to 10 to the minus 14. We don't bother to say 1 times 10 to the minus 14. So that may happen quite a bit, and that's okay. It might make your math teacher mad, but let's get them, okay? All right, so what's this going to be? Okay, well, yeah, you got it. This is minus 4, so you need to have 1 times 10 to the minus 10 to be the hydroxide ion concentration, because you add those two up, and you get that. So with that, ladies and gentlemen, we're going to stop here now. Now, the worksheet, next one we're going to work on after the video. Refer back to these and help you out. So with that, thank you, everybody. Let's watch an awesome video. It's Cosmos. It's called The Clean Room. And there's kind of zombies kind of sort of present in a weird temporal way. Okay, now if I can figure out how to stop this recording.